This week in our study of Lipschitz functions, it'll actually be helpful for us to first take a look at affine maps and how they distort Hausdorff measure. To do this, we'll introduce the singular value decomposition, or SVD. So suppose we have a n by n matrix M. Then singular value decomposition says that there is a n-dimensional orthogonal matrix U, a m-dimensional orthogonal matrix V, and a n by m diagonal matrix sigma, whose diagonal entries are lambda 1, lambda 2, down to lambda m, all non-negative and in decreasing order, so that m can be written as the combination of U sigma V transpose. So what do we mean by a n by m diagonal matrix, so a non-square diagonal matrix? Well, the case that we're going to be looking at, n is going to be at least the integer m. So sigma is going to have n rows and m columns. And so what we mean by a diagonal matrix of this form is that really there is a square diagonal matrix followed by several rows of zeros. So geometrically speaking, what the singular value decomposition says is that given a linear transformation M going from Rm to Rn, we can decompose the linear transformation into three different transformations. So the first one is just a rotation. So it takes a vector x and then rotates it without changing its size. The second transformation is the diagonal transformation, and all this does is that it skews or stretches points along the coordinate axes. So if lambda 1 is the first diagonal entry, so if this is E1 and lambda 1 is the first diagonal entry, it's going to take E1 and stretch it to lambda E1. And if lambda 2 is the second diagonal entry, it's going to stretch or contract the vector E2 by a factor lambda 2. And moreover, because sigma also has could have several rows of zeros in it, what this also does to the vector x is that after performing these stretchings, it adds on several zeros to the vector x so that the resulting vector lies in Rn. And then the final transformation is another rotation U that now rotates all the vectors without changing their sizes. The diagonal entries lambda 1 down to lambda m are called the singular values of m. And notice that the largest singular value is the same as the norm of the matrix, or the operator norm of the matrix, and which is also the same as the Lipschitz constant of the linear transformation. Then the smallest singular value is the lower Lipschitz constant, or in other words, m of any vector x is going to have norm at least lambda m times the norm of the vector x. So in particular, if the smallest singular value is positive, that means that the linear transformation is by Lipschitz. So using the singular value decomposition, we can actually get a precise formula for how Hausdorff measure is transformed under an affine map. So suppose we have an affine map A going from Rm into Rn, where the target space has dimension at least the dimension of the domain. And let's suppose that we have a subset E of Rm, and let lambda 1 through lambda m denote the singular values of the derivative of A. Then the Hausdorff measure of the image of E under A is equal to the product of the singular values times the Hausdorff M measure of E. You can show that the product of the singular values is actually the same as the square root of the determinant of the product of dA transpose with dA. So let's go through the proof. So first of all, notice that translations don't affect the Hausdorff measure of a set. So without loss of generality, we can subtract the value of A at 0 from A, and then we'll get a linear map. So without loss of generality, we can assume that A is a linear map and equals its derivative. By the singular value decomposition, that means that we can decompose A into a product of an orthogonal transformation with a diagonal matrix with another orthogonal transformation. Now, since orthogonal transformations are isometries, that means that they're 1 by Lipschitz, which means that they don't change Hausdorff measure, which means that all the change in Hausdorff measure occurs in the diagonal matrix. So without loss of generality, we'll just assume that A is equal to the diagonal matrix. Now, again, recall that our diagonal matrix sigma is of the form, it's equal to a square diagonal matrix followed by several rows of zeros. So that means that really the change in measure is all happening in this diagonal matrix here. So, or that is to say, the act of adding zeros onto a vector is also itself an isometry. So without loss of generality then, we'll actually assume that A is a diagonal matrix, and in particular, a square diagonal matrix. So it's going from Rm to Rn. Now, in this case, then it's clear that the equation above holds. So this is easy to visualize in 2 dimensions. If we have a square, for example, then let's say it's an A by A square, then if lambda 1 is the first diagonal entry of sigma, or first diagonal entry of A, that means that it's going to stretch vectors along the x1 axis by a factor lambda. So it's going to stretch the square by a factor lambda. And if the second diagonal entry is lambda 2, that means that it's going to stretch or contract vectors in the x2 direction by a factor lambda 2. And so then the resulting rectangular prism that we get after this transformation is going to have base lambda 1a and height lambda 2a. And therefore, the measure of this square has changed by a factor lambda 1 times lambda 2. So because it holds for cubes, then that means that it holds for open sets, because then we can write open sets as unions of cubes. And then thus, because we can approximate the measure of any other set by a decreasing sequence of open sets, this implies that it will hold for all Borel sets and hence for all sets by Borel regularity.